Hello everyone, welcome to another video of the course. In this video, we are going to solve the problem number 6 and so on. Like before, depending on how much time we have today. But today, I try to solve more problems. Okay, so we used the ANSYS Maxwell, and for example, for this problem, we don't have dimensions, and this is similar to previous one. This one you can repeat it yourself. So just I want to use MATLAB and simpler, but you can generate the ANSYS Maxwell model. So let's solve problems faster so you can learn the procedure for solving more problems. Anyway, here is the problem 6. A two-pole generator, as shown in this figure, has a magnetic circuit with the following dimensions. Each pole is made of cast steel. This is the material of one pole. The magnetic length is 10 centimeter and the cross section is 400 centimeter square. The air gap, the air gap length is 0.1. The cross section is the same as this one. Here, as you can see, we have two air gaps. This is a two-pole machine. The armature, this one, is made of a silicon steel sheet. The average length is 20 centimeter and the average cross section is 400. So the average cross section is the same as this one and this one. But why we have this term, the average length and average cross section? So here, let me copy the image of the structure. Here is the structure of the magnetic circuit that we have. We have these two field coils, this pole and this yoke, the back iron of the stator, and this is the armature. Or this is the stationary part, the stator, and this is the rotor part. So this is the stator and this is the rotor or armature. So let me explain this one first. I'm going to set the direction of the excitations for this coil arm regions. Here in this problem, we have two coils, two field coils that are identical. So these two coils are used to magnetize the structure, to magnetize the generator. So let's consider that the current in this coil arm region is out of the paper. So for this coil arm region, the direction of the current is into the paper, and therefore the field generated by this coil is in this direction. What about this one? For this coil, the direction of the excitation must be in this direction because the field that is generated by this coil should be in this direction. Okay, so this is the direction of the flux density vectors. We have a two-pole machine. and the direction of the excitation for this coil arm region is into the paper. Otherwise, right, the field that is generated by this coil is in this direction, is not a useful structure. So let's plot a flux line. When we excite these two identical coils, we will have this magnetic field. So this is one flux line, and you know that after excitation of the field coils, we can build up a field that is passing through this gap, through the armature, this pole, and the back iron, the stator yoke. And here, this is another flux line. So, here is the direction. As you can see, for air gaps, we can consider that the flux lines are in these directions, right? Between the armature and the pole. So the length of these flux lines are the same. And here you can see the length of the air gap, 0.1 centimeter. But inside the armature, as you can see, the length of flux lines are different. Okay, so we have also different cross sections. If you look at armature here, for this cross section, for this cross section, or this one. So this is the average length and the average cross section. You know how to calculate the reluctance for a cube, right? If we have a cube of a magnetic material with this cross section A and this length L, if we have a uniform magnetic field inside this cube, we can calculate the reluctance. That is equal to L divided by the permeability of the material times A. So this is a simple equation. But for more complex structures, actually this armature is like a solid cylinder. You can use the equations, the integral versions, and calculate integrals, consider elements. For example, you can consider this as a reluctance, this one, like the models that we have in electromagnetic, right? So you have a distributed model, you can calculate integrals, and finally calculate the reluctance of the armature. But do we need to do that? No, because in this problem, the average length and the average cross section are given. So simply, we can calculate the reluctance of the armature using this equation. So every term in the problem is also important, and you should distinguish between this and this one. But still, we can use the same equation, this one, for calculation of the reluctance. Anyway, and here we have yoke. Yoke is the back iron of the stator. This is the structure. So let me visualize it better. Again, copy this. This is the pole. and this is the yolk. So I can consider this as pole region, this one, this is a pole, and this is a right yolk that we have for this structure. And here, this is the average. If I place this circle in the middle of the back iron, the stator yolk, okay, the perimeter of this circle is the mean circumference, that is equal to 160 centimeter, and the average cross section is 200 centimeter square. The cross section of the yolk, this cross section, right? The length that we have here is half of this one, and this one. So here cross sections are equal, and this is half. So half the exciting ampere turn are placed on each of the two poles. Yes, these two coils are identical, and the half of the needed magnetomotive force is generated by this coil, and the other half is generated by this coil, and you know the direction of the excitations. So throughout the magnetic equivalent circuit, okay, B, how many ampere turns per pole are required to produce a flux density of 1.1 Tesla in the magnetic circuit? Use the magnetization curves for the respective materials and finally calculate the armature flux. I am going to solve this problem using two methods. Finally, we can compare the results. Here is the part A, drawing the magnetic equivalent circuit. So in this figure, you can realize the magnetic equivalent circuit by following the flux lines. So when we excite these two coils, considering these directions for excitation, we will have these flux lines, and let's draw the reluctances in front of the field. We have one reluctance here. This is the armature reluctance. We have one reluctance here, air gap. One reluctance here. We have one reluctance for this pole and another reluctance for this pole. Finally, we have one reluctance for this yolk, half, and another reluctance for this side of the yolk. And we have two magnetomotive force sources. So finally, you can draw this magnetic equivalent circuit. This is the reluctance of the armature. This is the reluctance of the gap. These two are equal. These two sources are equal. The reluctance of the pole, and we have two yolks. So, right, this is the first part, and we derived this equivalent circuit by knowing the correct directions for excitations. So, part B, how many ampere turn per pole are required to build up 1.1 Tesla? We have these two materials. We have these two materials in our problem. we have silicon sheet steel and cast steel. Cast steel and silicon steel, these two materials. So if we want to have 1.1 Tesla in different locations of the motor, how much magnetomotive force is needed? What should be the value of the magnetic field intensity? We can interpolate the value of the magnetic field intensity from this figure. So if we consider 1.1 Tesla for the cast steel, the value of H is 800 according to this graph. And the value of the H for the silicon steel sheet is equal to this one. We don't have HB curve data to use interpolation in MATLAB. So approximately we can say that this is equal to 280. So here you can see the code for the problem 6, and I consider this inputs. This is the cross section area A 400 centimeter square. I considered this unit, so I multiplied it by 1e minus 4. This is the permeability of the air, and this is the magnetic field intensity in Yoke and pole. 800 for the armature, 280. We interpolated these values considering these curves, these HP curves. So, how much is the value of the magnetic field intensity in air gap? The aim is to have 1.1 Tesla in air gap. So 1.1 Tesla divided by mu 0 is equal to this one. This is the value of H in air gap. How we can calculate the total magnetomotive force needed for excitation for magnetizing this two-pole generator? We can calculate reluctances and solve the circuit, calculate the flux in armature, okay, according to this, and there will be one unknown, that is current, and finally based on those equations we can find the value of the current. But we have another way, because we need to calculate the needed MMF, the magnetomotive force. We can use this equation, integral of H dot dl is equal to Ni. So if I consider this flux line on one side only, let me delete this image and copy it again. I want to represent the flux line that we need to calculate this integral. I am going to consider this flux line. This is in the middle of the stator yoke. Okay. So, if we consider this integration path, to calculate integral of h dot dl, we can use this equation. H yoke, L yoke plus 2 times H pole, L pole plus 2 times H gap, L gap plus H armature L armature. That is equal to 2 times Ni. Ni is the magnetomotive force of one coil. So here, what is the value of Ly? We know the magnetic field intensities. Ly is this one, okay? We know the mean circumference. So Ly is the half of this mean circumference, right? That is 160 divided by 2. And we have L pole, L gap, L armature. So finally we can use this equation to calculate the magnetomotive force. Here are values. This is the value of the H gap, 1.1 Tesla divided by mu 0. The value of the magnetic length of the pole magnetic length, 10 centimeter. The air gap, 0.1, armature 20, mean circumference is 160 divided by 2. This is the length of the flux in the stator uke. We consider this integration path. So what are the outputs? The total magnetomotive force is equal to this one. Okay, this is the terms that we have here. Because the unit of the length in these terms is centimeter, I multiplied the total summation by 1e minus 2. So we can calculate the total magnetomotive force, and finally we can calculate the flux, the armature flux, using this equation. We know the value of BA, so we can calculate the phi A. That is 1.1 Tesla times the cross-sectional area. This one. So if I run the code, here you can see the numbers. This is the total magnetomotive force, MMF. That is around 2,600 ampere turn per meter. And the value of the phi armature is 0.044 Weber. So now let's calculate the value of reluctances and solve this magnetic equivalence circuit and calculate the armature flux and compare with the number that we calculated it here. Yes, simply we can write these equations. This is the reluctance of the air gap, the permeability of the armature, reluctance of the armature, permeability of the pole, reluctance of the pole, and this is the reluctance of the uke. So we can calculate the armature flux using the magnetic equivalence circuit method. That is equal to this one. The total magnetomotive force divided by the reluctance, right? What reluctance? We should simplify this circuit. The reluctance of this side of the uke is in parallel with this side. So this is the total MMF divided by 2 times reluctance of the gap, reluctance of the armature, 2 times reluctance of the pole, plus reluctance of the uke divided by 2. These two are in parallel. So here you can see the value of the phi A, the flux in armature calculated by the magnetic equivalence circuit. That is the same. Anyway, so now let's solve this problem using the ANSYS Simplorer and compare. I generated this equivalent circuit. Here you can set the value of the reluctances and solve the problem. So this is the magnetomotive force divided by 2. Let's copy this number, paste it here. The reluctance of the armature is this one. This is the armature reluctance. The reluctance of the gap is this one and this one. The reluctance of the pole, the magnetic pole, here and here. Finally, the reluctance of the yoke is this one and this one. So we have set the value of reluctances and let's solve the problem. Not transient, DC solver, analyze. So we can compare the numbers that we calculated in MATLAB with ANSYS Simplorer. This is good to double check the numbers. This is the reluctance of the armature, flux 0.044. The same number that we calculated for the flux here. This is great, right? We used the different methods, different softwares and validated our calculation. So let's go for the next problem. Problem 7. So a two-pole synchronous machine as shown in this figure has the following dimensions. Each air gap length is 2.5 millimeter. The cross-section area of pole face is 500 centimeter square. This is the pole face. This is the thickness of the air gap. The total number of turns is 500. We have excitation coil here. This is a synchronous machine, a two-pole. This is the field winding. And the value of the current is 5 ampere. The permeability of the core is infinite. We have ideal iron cores. Draw the magnetic equivalent circuit and find the flux density in the air gap. This problem is similar to the previous one. Again, you know that when you excite this coil, this is the coil, okay? When you excite this winding, the direction of the current is in this direction. We have this flux line, okay? This is a two-pole machine. And this flux line that is in this direction. So, because the reluctance of the iron is 0, we have ideal iron. Only we have two reluctances. One air gap reluctance here, another air gap reluctance here. So considering these flux lines, we can draw this equivalent circuit. So this is the total magnetomotive force N times I, and we have this R gap here and R gap here. This is the length of the gap divided by mu 0 area of the gap. And finally, we can calculate the flux density in air gap, knowing the flux in air gap using this equation. We have the pole face and the air gap length. So let's write the MATLAB code for this problem. I can copy this for the problem 7. We can write the area of the gap is equal to 500. This is the area of the gap. 500 is the pole face area. Pole face area. The length of the gap is 2.5. The air gap length. Air gap length. The unit is millimeter. And the number of turns 500. This is n equal to 500. The number of turns, coil turns. This is the field winding. And the value of the current is 5 amps. This is the coil current. Coil current, that is equal to 5. The unit is ampere. We can calculate the reluctance of the gap. This is the right output section, reluctance of the gap. Maybe we can copy the this line here. Air gap reluctance is equal to L gap times 1e minus 3, because this is in millimeter. 2.5 units are important. And this is the area of the gap. The unit is meter. This is mu 0. And we can calculate the phi gap. This is the flux in the gap, N times I divided by 2 times reluctance, right? These two are parallel and these two reluctances are in series. So 2 times reluctance of the gap. This is flux in air gap. The unit is Weber. Finally, we can calculate the flux density in air gap. That is phi in the gap divided by this area. This is the flux density in air gap. The unit is Tesla. So let's run. The value of the B gap is 0.628. And here you can see the value of the flux in air gap. That is equal to 0.0314. Let's check these numbers with this is an odd problem. We should have the solution here. Yes, 1.7.628 Tesla. We did the math correct. So, can we solve this problem in ANSYS Maxwell or no? We don't have enough dimensions, but I am going to consider a radius, a counterpart problem and solve just to visualize. Okay, so you can repeat the same thing. Let's save the model. this project and generate a new project here. This is the problem number 7. So let's add one ANSYS Maxwell model. How we can generate this geometry, okay. I don't want to consider slots. Okay, here you can see the field winding is visualized here. So I can draw one circle first, like this. So the radius of this circle is important. Let's write here the radius of the gap equal to, let's consider for 40 centimeters, or we can consider a lower number. The radius of the gap 25, okay. The radius of the gap, or maybe lower, 20. We should adjust numbers. So then we can generate, right, these parts, right, parts for this side and this side, and subtract it from the rotor. So here we can draw a rectangle on this side and another rectangle and subtract it. So this is the procedure, but I think this one is better. This one is better. Let's draw a line, a center point arc, again a line, and close it. Why? Because we can adjust this angle. Okay, so this is easier. So here the x coordinate of this point is radius of the gap. This arc, let's consider it equal to 30. So the pole face arc will be 60, right, according to this image. And this is actually, we need to consider the same height, okay, for the coordinate of this point, 160. So this is r gap times sine of pi divided by 6. So yes, this geometry, okay, this is this height, this coordinate that I considered for the y coordinate of this point. Okay, so yes, we can duplicate and mirror and build up the full geometry for the rotor. So now let's subtract this rectangle from it. Here I need to consider one value for width of the coil, okay, for width of the coil. So this rectangle, the y position is equal to this one minus width of the coil minus 1 centimeter. Width of the coil, consider it equal to 5 centimeter. So we need to specify the x size and the y size. The y size is the width of the coil. We can consider 2 times 2 And the x coordinate, I can consider this times cosine minus 5 centimeters. This 5 is this is arbitrary number. Let's consider 3. And here we can modify the width of the coil. For example, if I consider 3, yes, this is better. So select this one, subtract. And now we can select this object, duplicate mirror, these two unite, duplicate mirror, these two unite. Okay, so we constructed the rotor. And here we can draw these two circles. This is circle 1 is the radius is r gap plus 2.5 millimeter. This is the air gap length. We need to add up this. For this circle is r gap plus 2.5 millimeter plus a thickness for the back iron. Let's consider it equal to 4 centimeters. This geometry. Or even we can consider a higher number. Let's consider 6. Okay. This circle, select this circle and subtract. We have created the iron cores for the rotor and stator. So, in this case, if I draw a rectangle here, I can define excitations and calculate the electromagnetic field. So let's draw this. What is the x and y coordinates of the corner point? You know, this is this one plus 1 centimeter. The x size is important and the y size. Y size is the width of the coil. Okay, so for this rectangle that we created, these are dimensions. You can find the dimensions from the history of this subtraction. This is this one minus width of the coil minus 1 centimeter. So we can use this one just plus 1 centimeter. This is x size. So here, this is this one minus width of the coil. This is x size minus 1 centimeter again from both sides, and this is the y size. So I considered this coil arm. Finally, we can duplicate and mirror it, unite. Here, duplicate, mirror, but we don't unite. We need to define separate excitations. So here, our model is parametric. For example, if I change the radius of the gap to 25, the model will be updated automatically. So now let's define excitations. For this coil arm region, the direction of the current for this one is into the paper, and for this one is out of the paper. So the value of N is 500, the value of the current is 5. So let's select this one, the excitation current is 500 times 5 ampere. The direction of the current is negative. For this one is this, the direction of the current is positive. Yes. So let's change the colors. And here we have iron. Like before, we need to increase the value of the permeability. These two are copper. And we need to draw enclosure. Here I draw this enclosure. Let's change the transparency. So how to set the radius of this enclosure? The radius of this enclosure should be higher than the outer radius of the stator, but not too much higher. This is the solution region. So we can select this edge and apply the vector potential boundary condition. That's all. So we can add the analysis setup and solve the problem. So let's analyze and check. Problem, right? Solution completed. We can select all faces, plot B vector, the direction of the magnetic field. So let's reduce the spacing. Okay. And maybe also you can modify the size lower. Yes, this is much better. Reduce the spacing. And again, reduce the size of the vectors. Yes, this is a great graph. You can see the direction of the field. And also we can plot the flux lines. So delete this one. Select the faces again to plot the flux lines. Here we have these flux lines that we discussed here. So I want to, this is one air gap at this side. So I want to plot this variable. If we consider the cylindrical coordinate system, we have this B gap, the radial component. Okay, so this is the flux density vectors in air gap. I want to plot BR versus theta. Theta is the circumferential position. Okay, so we can add a circle here in the middle of the air gap, this circle 4. This is the radius of the gap plus 2.5 millimeters divided by 2. Cover lines, no. Just I want to have an edge object. So let's solve the problem again and plot the result. So if I select this edge, I can plot B on it, B vectors. So here in this air gap, the flux density vectors are in this direction. For this air gap, flux, right, is in this direction, the flux densities vectors, right? So how we can plot the radial component versus the theta? If you consider this theta, this is the theta, right? In the cylindrical coordinate system, the angle coordinate. So we can here in the field calculator, we can select b vector, bx, by 0, translate it to cylindrical coordinate system, and then select the first component. You know that the first component of a vector in cylindrical coordinate system is the radial one. So add BR. Now I can generate this field plot. I can select circle for the distance. This is BR. Okay. So for this pole, the direction of the flux, right, is in this direction. The average value is positive. The average value here is negative. Okay, we have two poles. So let's consider ideal iron. The permeability of the iron, consider it equal to 100,000, ideal case, and adjust the value of the radius of the air gap to get this air gap area. I want to calculate the flux density. The flux density is 0.6283. How much is the flux density here? The maximum value 0.59. So let's repeat the analysis again. This is the value of the flux density. The maximum one is 0.63. So if I calculate the average absolute value, the average value of absolute value of this function, you can see the mean value. This is the maximum value. Compare it with this number, 0.628. Okay, for this ideal problem. So how you can measure the pole face area? You can select this edge, and measure the length. So here you can see the length of this edge, 209, around 21 centimeter. If we are going to get this area of the gap, that is 500, how much is the depth of the problem? Is 500 divided by 21. The depth of the problem is 23.8. So if we are going to get the same pole face area, this is the depth of the problem in this case. We can modify it. I want to calculate the value of the flux in air gap, okay, and compare with the number that we have here. So this is the flux, 0.0314. How we can calculate the flux? If we calculate the flux linkage to this coil, we know that the flux linkage is equal to n phi. And this is the phi. So we can calculate phi. In ANSYS Maxwell, to calculate the flux linkage, you need to define one excitation matrix here. So I define this matrix. This matrix has two coil arms. I select these two. The number of turns is equal to 500 for this region and this region. Then we can select these two and group them. Okay, so you can see this matrix that we defined. This is our coil. We are going to calculate the flux linkage for it. So here, if I repeat this analysis setup, I can draw this from the create magnetostatic report data table, mag flux. This is the flux linkage to this coil. But this flux linkage is calculated considering the depth of the problem equal to 1 meter. We didn't set the depth of the problem for the software. Okay, so this is the magnetostatic simulation for one cross section of the motor. So we need to include the depth of the problem in our calculations. You know, as long as we increase the depths, we have more and more flux. So the value of the flux varies linearly when we change the depths. The correct depth in our case is equal to this one. So I can copy this, multiply this by this centimeter divided by 1 meter. Apply trace. Here you can see the total flux linkage. So phi gap times 500 is 15.7, and we got this number. Because here for the pole phase, I need to consider the exact number. So let's recalculate it again. This is pole phase. So select this edge. What is the value of the pole phase? Is this one. This is millimeter divided by 10. Right, this is centimeter. Is close to 21. I think we divided 500 by 21 also. So anyway, these two numbers are okay close, and maybe we need to modify some dimensions because we use the arbitrary numbers. We can adjust the dimensions to get the exact numbers. Anyway, so look, if I change the radius of the gap to, for example, 17, and repeat the example, I want to adjust the coordinates to get the same numbers. So in this case, the length is this one, 17.8. So here is 0.8, 28 to get this area. This is 28. So let's clear the solutions and repeat the example. Okay, so this is the flux linkage. You can try other dimensions. And finally, if we divide this by 500, this is the value of the air gap flux, 0.34. Phi gap is 0.314. The numbers that we calculated using this ideal case, ideal magnetic equivalent circuit considering infinite permeability for the iron. Anyway, so you can repeat this great example in ANSYS Maxwell, change dimensions and compare results. And as you can see, how this is great for visualizing the data. In this case, in this ideal case, the waveform is rectangular, right? These sharp corners. But in practice, here as you can see, this is not sharp. So maybe the difference that we have is because of this. Anyway, you can think about it. So now let's continue and go for the next problem. Okay, so the problem 8 of the chapter 1. The electromagnet shown in this figure can be used to lift a length of a steel strip. This is a steel strip, and the aim is to generate a force and lift this steel strip. The coil has 500 turns and can carry a current of 20 amps without overheating. This means that this coil is actually the thermal design is considered in it, and we don't worry about the overheating. It can tolerate this current 20 amps. The magnetic material has negligible reluctance at flux densities up to 1.4 Tesla. So as long as the flux density is below this number, the magnetic reluctance is negligible. Okay. Determine the maximum air gap for which a flux density of 1.4 Tesla can be established. With a coil current of 20 amps, neglect magnetic leakage and fringing of flux at the air gap. So here, this is the case. We have this structure, and you know that when we excite this coil, we will have a field in this direction. So this is one flux line, and here we have one flux line, and we have a flux line path here. So dimensions are given. The width of the air gap, the width of this tooth is the same as this one, 10, 10. This is 20. Okay, so units are not given. I think the units are centimeter, or even are the units important or not? Okay, so this is a question. Depends. Let's check. Here we can draw this equivalent circuit because the reluctance of the iron parts is 0. Only we have 3 reluctances for air gaps. We have one air gap reluctance here, one here, and one here. And we have this magnetomotive force source, Ni. We can calculate R gap 1. The value of the R gap 2 for these sides are the same. The value of the phi in this gap, gap 2, this is also gap 2, is half of the gap 1. What is the reason? Because the value of the flux density in air gaps are the same, and this is half of this one. So the half of the flux generated by this coil goes through here and the other half goes through here. We can write this equation. The phi in this side air gaps is half of the flux in the middle air gap. According to this magnetic equivalence circuit, we can write Ni is equal to R gap phi gap 1 plus R gap 2 phi gap 2. This one. So phi gap 2 is phi gap 1 divided by 2. Okay. And what is the value of the reluctance for the air gap 1 is equal to L gap divided by mu 0 A times, this is the value of the flux, B gap times 2 times A divided by 2. What is A? A is the area of a side air gap. So the area here, area of this cross section is 2 times A. So B gap times 2A is the total flux in the air gap 1, and this is the total flux, right, in this air gap. Excuse me, I need to cut this equation, place it here according to the above equation. So this is the reluctance of the gap 1, L gap, divided by mu 0 2 times A times B gap times 2A, total phi gap 1. And this is for the gap 2. So in this equation, we know the value of N, we know the value of I, we know the value of mu 0, the value of the B gap. We don't need to know the value of area. Okay. So finally, using this equation, we can calculate the value of the L gap. So how? This is the equation, and this is the area 2 2, again this area, this 2. So L gap is equal to Ni times mu 0 divided by 1 B gap here and 1 B gap here, 2 times B gap. So let's implement this equation in MATLAB for the problem 8. Again, here we have mu 0. This is the desired air gap flux density, 1.4. This is desired air gap flux density. The unit is Tesla. And we know the number of turns is equal to 500. The value of the current is equal to 20. This is the coil current, 20. And we can calculate the value of the L gap using this equation. So output, the value of the L gap is equal to N times I times mu 0 divided by 2 times B gap. So if I run the code, this is the value of L gap. If I multiply it by 100, it is 4.48 millimeters, right? So this is the air gap size. The unit is millimeter. I multiply this by 183. So this is the maximum air gap flux for which this flux density is established. So when the air gap length is lower than this one, we have a higher value for the flux density. And when it is higher, we have a lower value for the flux density. The unit of these numbers is not important as you solve in the calculations that we had. Just we need B gap and these variables, these numbers. Anyway, you can repeat the same procedure and realize the flux path throughout the circuit and try this example. I don't generate the ANSYS Maxwell model. We did it for previous examples, but you can generate the ANSYS Maxwell model, generate the flux density plots, right? It will be a good practice. So, I think the time of the video is high, this one. So let's continue solving the problem 9 in the next video. Thanks for watching.